Welcome to this problem walkthrough. Today, we'll be tackling problem number 1356, sort integers by the number of 1 bits. In this session, we'll explore the problem statement, break down the approach step by step, and discuss its computational complexity. Let's get started. In this problem, we're tasked with sorting an integer array, RR, based on the number of 1 bits in each integer's binary representation. The sorting should be done in ascending order. If two integers have the same number of 1 bits, we resolve the tie by sorting them according to their numerical value in ascending order. For example, if two numbers both have 2 bits set to 1, the smaller numerical value will come first. The input is an array of integers, where the size of the array can range from 1 to 500, and the integers themselves can range from 0 to 10,000. The output will be a new array sorted according to the described rules. This means we need to carefully analyze both the binary representations of the numbers and their values to achieve the correct ordering. To better understand the problem, let's look at an example. Suppose the input array is 0, 1, 2, 3, 4, 5, 6, 7, 8. The output should be 0, 1, 2, 4, 8, 3, 5, 6, 7. To understand why, we start by converting each number into its binary representation. For instance, 0 in binary is 0b0, which has 0 bits set to 1. The number 1 is 0b1, which has 1 bit set to 1. Similarly, 2 is 0b10 with 1 bit, and 3 is 0b11 with 2 bits. We repeat this process for all numbers in the array, counting the number of 1 bits in their binary forms. Once we have this information, we sort the numbers first by the count of 1 bits and, in cases where the counts are the same, by their numerical value. Continuing with the explanation, the binary representation of 4 is 0b100 with 1 bit, 5 is 0b101 with 2 bits, 6 is 0b110 with 2 bits, 7 is 0b111 with 3 bits, and finally, 8 is 0b1000 with 1 bit. When we sort these numbers by the number of 1 bits, the order becomes 0, 0 bits, 1, 1 bit, 2, 1 bit, 4, 1 bit, 8, 1 bit, 3, 2 bits, 5, 2 bits, 6, 2 bits, 7, 3 bits. Notice how the numbers with the same number of bits are sorted by their numerical value. For example, numbers with 1 bit, like 2, 4, and 8, appear in ascending numerical order. Now consider another example where the input array is 1024, 512, 256, 128, 64, 32, 16, 8, 4, 201. The output in this case is 1248, 16, 32, 64, 128, 256, 512, 1024. Let's break down why this is the correct result. For each number in the array, we calculate the binary representation and count the number of 1 bits. For instance, 1 is 0b1 with 1 bit, 2 is 0b10 with 1 bit, 4 is 0b100 with 1 bit, and so on. All the numbers in this array have exactly 1 bit set to 1. Since the number of 1 bits is the same for all elements, they are sorted purely by their numerical value in ascending order. Let's look at one more example for clarity. Suppose the input array is 10, 100, 1000, 10,000. The output is 10, 100, 10,000, 1000. To verify this, we calculate the binary representation and count the bits. The number 10 is 0b1010 with 2 bits, 100 is 0b1100100 with 3 bits, 1000 is 0b1111101000 with 6 bits, and 10,000 is 0b100111001000 with 5 bits. Sorting these numbers by the number of 1 bits, we have 10 first with 2 bits, followed by 100 with 3 bits, then 10,000 with 5 bits, and finally 1000 with 6 bits. This ensures the correct ordering based on the rules. Finally, there are some important constraints and edge cases to keep in mind. The array size can range from 1 to 500, and each element in the array can range from 0 to 10,000. For edge cases, if all elements in the array are 0, the output will simply be 0, since 0 has 0 bits set to 1. If all elements have the same number of 1 bits, the result will just be the array sorted numerically. Additionally, for large inputs with many integers close to the upper limit of 10,000, your solution must handle the sorting efficiently. The smallest possible input is an array with a single element, like 0, which directly returns 0 as the output. To solve this problem, we can start by considering a straightforward brute force approach. The idea here is to calculate the number of 1 bits for each integer in the array and then sort the array based on this count. If two integers happen to have the same count of 1 bits, we use their numerical value as a tiebreaker. This can be implemented using a helper function, which we can call count_ones, that calculates the number of 1 bits for a given number. Once we have this helper function, we can use Python's built-in sorted function, providing a custom key, a tuple, count_ones, x, to ensure that the primary sorting is done by the bit count, and the secondary sorting by the numerical value. However, this approach has some trade-offs. While it's simple and easy to understand, it can become inefficient when working with very large arrays because the count of 1 bits is repeatedly computed for every number. In terms of complexity, counting the bits for all numbers takes n*k, where k is the maximum number of bits in the binary representation of a number, and sorting the array adds another n*log n. Hence, the overall complexity is n*k plus n*log n. While this approach is straightforward, its inefficiency highlights the need to optimize further, especially for larger datasets. A more efficient strategy involves using memoization to avoid redundant computation of the number of 1 bits. Instead of calculating the bit count repeatedly, we can pre-compute these values for all numbers up to the maximum value in the array. This can be done using dynamic programming with the formula count_bits, x equals count_bits, x1, plus xn1. This formula works by leveraging the bit count of smaller numbers that we've already computed, making the process linear with respect to the range of values. Once the pre-computed values are available, we can use them directly as the primary key for sorting, with the numerical value as the secondary key. This optimization reduces the computational overhead significantly. In terms of complexity, pre-computing the bit counts has a cost of m, where m is the maximum value in the array, while sorting remains n*log n. Therefore, the overall complexity becomes m plus n*log n. This approach scales much better for large arrays compared to the brute force method. Another alternative worth considering is leveraging Python's built-in functions like bin and count to directly calculate the number of 1 bits. While this simplifies the implementation, since we can use bin x.count1x as the sorting key, it doesn't eliminate redundant computation. Consequently, it's slightly slower than memoization for larger arrays. This trade-off between simplicity and efficiency makes memoization a more robust choice for this problem. The optimized approach using memoization is ultimately the most effective strategy for this problem. It balances efficiency and scalability by reducing redundant computations while keeping the sorting step efficient. Pre-computing the bit counts is particularly powerful because it transforms a repetitive operation into a single linear pass over a fixed range, leveraging the pre-computed results during sorting. This insight allows the algorithm to handle larger inputs more effectively. On the other hand, the brute force approach, while easy to implement, is inefficient due to the repeated computation of 1 bits for each number. Similarly, using Python's built-in functions like bin and count is simpler but slower than memoization for large datasets because it doesn't avoid redundant operations. The optimized approach does introduce an additional memory requirement to store the pre-computed values, but this trade-off is well worth it for the time savings it provides when working with larger arrays. In terms of complexity, pre-computing the bit counts takes m, where m is the maximum value in the array, while sorting the array takes n*log n. This results in an overall complexity of m plus n*log n, which is efficient and scalable. Here is the implementation in Python. We first calculate the bit counts for all numbers up to the maximum value in the array using dynamic programming, and then sort the array using these pre-computed values as the primary key and the numerical value as the secondary key. In this problem, the goal is to sort an array of integers based on the number of 1 bits in their binary representations. If two integers have the same number of 1 bits, we resolve the tie by sorting them in ascending numerical order. To begin, we clearly define the input and output. The input is an array of integers, and the output is a sorted version of this array. The sorting is done in 2 stages, first by the count of 1 bits, and second by numerical value for ties. To achieve this, the first step is to compute the number of 1 bits for each integer in the array. Using Python, for instance, the bin x.count1 operation gives the count of 1 bits in the binary representation of any integer x. We then pair each integer with its respective 1-bit count, creating tuples like count of 1 bits x. This allows us to use the count as a sorting key later, making the sorting process straightforward and efficient. Next, we use a stable sort algorithm to order the array based on 2 keys. The primary key for sorting is the count of 1 bits in ascending order, ensuring that integers with fewer 1 bits are placed earlier in the array. The secondary key, numerical value, is used to break ties between integers that have the same count of 1 bits. A stable sort is crucial here because it guarantees that the secondary key preserves the relative ordering of elements with equal primary keys. After the sorting step, we extract the original integers from the sorted pairs to construct the final output array. Each integer is taken from the second element of the tuple, and this forms the sorted array that meets the problem's requirements. The result is then returned as the output of the algorithm, completing the process. The key insights behind this algorithm make it both intuitive and efficient. First, calculating the number of 1 bits using the bin x.count1 function is a quick and reliable way to derive the primary sorting key. Second, by leveraging stable sorting, we ensure that the secondary key, the numerical value, is seamlessly applied to break ties without additional steps. This simplifies the implementation while guaranteeing correctness. From an efficiency perspective, the algorithm primarily relies on sorting, which is computationally efficient given that the sorting step dominates the overall complexity. For data structures, we use a list of tuples to store the pairs of 1-bit counts and integers. This structure is easy to manipulate and sort. The output is simply the sorted list of integers, extracted from these tuples, meeting the problem's specified criteria. Analyzing the complexity of the algorithm helps us understand its performance. For time complexity, calculating the number of 1 bits for each integer involves iterating through the array, which takes n, and for each integer, determining the 1 bits has a cost proportional to the bit length, k. This results in n*k, for the initial computation. The sorting step, which involves sorting the array of pairs, has a complexity of n*log n. Combining these, the overall time complexity becomes n*k plus n*log n. For space complexity, we need additional space to store the list of pairs, which requires n space. Therefore, the total space complexity is n, making the algorithm efficient in terms of both time and space, even for reasonably large input sizes. To solidify our understanding, let's walk through an example. Consider the input array ARR equals 5, 3, 7, 10. First, we calculate the number of 1 bits for each integer. The binary representation of 5 is 101, which has 2 bits. For 3, 11 also has 2 bits. The number 7, represented as 111, has 3 bits, and 10, as 1010, has 2 bits. This gives us the pairs 2, 5, 2, 3, 3, 7, 2, 10. Next, we sort these pairs. By the primary key, the 1-bit count, we arrange them as 2, 5, 2, 3, 2, 10, 3, 7. Then, using the numerical value as the secondary key, we refine the order to 2, 3, 2, 5, 2, 10, 3, 7. Finally, we extract the integers from the sorted pairs, resulting in the output array 3, 5, 10, 7. This demonstrates how the algorithm effectively sorts the input based on the criteria. The final output for our example is 3, 5, 10, 7. To ensure the algorithm handles various scenarios, let's consider some edge cases. For an empty array, there are no elements to sort, so the output is simply an empty array. When all elements have the same 1-bit count, like 2, 4, 8, the secondary key, numerical value, determines the order, producing 2, 4, 8. For negative numbers, the output depends on how we handle their binary representations. Signed integers may require additional consideration, but the logic can be extended to accommodate this. Overall, the algorithm is robust, handles edge cases effectively, and achieves the desired sorting criteria with efficiency and correctness, making it a reliable solution for this problem. This Python implementation solves LeetCode problem number 1356, sort integers by the number of 1 bits. The task is to sort an array of integers based on the number of ones in their binary representation, and for numbers with the same number of ones, sort them based on their numerical value. ###line by line explanation. 1. Class definition *. The solution class is defined to encapsulate the solution, as required by LeetCode's problem-solving framework. 2. Method definition *. The sort by bits method is defined. This function takes a single input, ARR, which is the list of integers to be sorted. 3. Key function definition *. Inside the method, a helper function bit_count_key is defined. This function takes an integer x as input and returns a tuple, bin x.count1 x. Here, bin x.count1 computes the number of ones in the binary representation of x. X is included in the tuple to ensure that numbers with the same number of ones are sorted by their numerical value. For sorting with custom key *, the sort method is used to sort the input array ARR in place. The key equals bit_count_key argument ensures that the sorting is performed based on the custom key function defined earlier. 5. Return statement *. Finally, the sorted array is returned as the output. ###why this works. The custom sorting key, bin x.count1 x, ensures that sorting is performed in two levels. 1. By the number of ones in the binary representation, primary sort. 2. By the numerical value of the integers, secondary sort, when the primary values are equal. ###complexity. Time complexity * sorting the array involves a time complexity of O, n log n, where n is the length of the array. Computing the binary representation and counting ones for each number takes O, k, time, where k is the average number of bits in the integers. Thus, the overall complexity is approximately O, n log n. Space complexity * the sorting is performed in place, so the space complexity is O, 1, excluding the input array. This implementation is concise, efficient, and adheres to the problem requirements, making it suitable for competitive programming and real-world applications. Here, we begin by importing the necessary Java utilities. The main function, sort by bits, takes an integer array as input. To facilitate sorting with a custom comparator, we first convert the input array into a list. This is achieved using a for each loop that iterates through the array and adds each element to the list. Next, we define a custom sorting logic for the list. This is done using the sort method, where we provide a lambda expression as the comparator. The lambda compares two integers, a and b, based on the number of 1 bits in their binary representations, which we calculate using the integer.bitCount method. If the counts of 1 bits are equal, we resolve ties by comparing the actual values of a and b using integer.compare. This ensures a stable and deterministic sort order. After sorting, the list elements are in the desired order based on the problem requirements. Once the list is sorted, we convert it back into an array, as the output format specified by the problem requires an integer array. This is done by creating a new array of the same length as the input array and populating it with the elements from the sorted list using a simple for loop. Finally, we return the resulting array as the output. This implementation ensures the input integers are sorted first by the number of 1 bits in their binary representation and, in case of ties, by their numerical value. The approach is efficient and leverages Java's built-in utilities like integer.bitCount and the sort method with a custom comparator to achieve the desired functionality. Let's start with the first example, where the input array is 0, 1, 2, 3, 4. The goal is to sort this array based on the number of ones in the binary representation of each number, and in case of a tie, sort by the natural order of the numbers. To do this, we define a custom key function called bit_count_key x that generates a tuple for each number. The first element of the tuple is the count of ones in the binary form of x, obtained using bin x.count1. The second element is just the value of x itself. Now, for each element in the array, we calculate its corresponding key. For instance, the binary representation of 0 is 0b0, which has 0 ones, so its key is 0, 0. Similarly, for 1, its binary form is 0b1, which has 1, 1, so its key is 1, 1. For 2, the binary is 0b10, also with 1, 1, making its key 1, 2. This process is repeated for all the elements, and the resulting keys are 0, 0, 1, 1, 1, 2, 2, 3, 1, 4. Once we have the keys, the array is sorted based on these tuples. The final sorted array is 0, 1, 2, 4, 3, which is the desired output. Now, let's look at the second example, where the input array is 10, 7, 3, 5, 1. Again, we use the same custom key function to compute the sorting keys for each element. For 10, its binary representation is 0b1010, which contains two ones, so its key is 2, 10. For 7, the binary form is 0b111, which has three ones, giving it a key of 3, 7. For 3, the binary is 0b11, with two ones, resulting in the key 2, 3. Similarly, for 5, the binary 0b101 has two ones, so its key is 2, 5. Finally, for 1, the binary 0b1 contains one 1, making its key 1, 1. With these keys, the array can now be sorted. The keys in order are 2, 10, 3, 7, 2, 3, 2, 5, 1, 1, and after sorting by these tuples, the array becomes 1, 3, 5, 10, 7. This is the final output for this example. Finally, in the third example, the input array is 100, 15, 8, 2, 6. As before, we calculate the sorting keys using the custom key function. For 100, the binary representation is 0b1100100, which contains three ones, so its key is 3, 100. For 15, the binary form is 0b1111, which has four ones, resulting in the key 4, 15. For 8, the binary 0b1000 has only one 1, so its key is 1, 8. For 2, the binary 0b10 also contains one 1, giving it the key 1, 2. Lastly, for 6, the binary 0b110 has two ones, making its key 2, 6. Once we have the keys, which are 3, 100, 4, 15, 1, 8, 1, 2, 2, 6, we sort the array using these tuples. After sorting, the array becomes 2, 8, 6, 100, 15, which is the desired output for this example. In this problem, we sort an array of integers based on the number of 1 bits in their binary representation. To analyze the time complexity, we first consider the key function, bit_count_key. For each integer x in the array, the bin_x function converts the number to its binary string form. This operation takes log x time because the length of the binary string corresponds to the number of bits required to represent x. Next, the count 1 operation scans this binary string and counts the occurrences of 1, which also takes log x time. Combining these steps, the key function bit_count_key x has an overall time complexity of log x. Now, the sorting step uses Python's timsort algorithm, which has a base time complexity of n log n for an array of size n. Since the custom key function is called during each comparison, the sorting process introduces an additional log x factor for each element. As a result, the total time complexity for sorting becomes n log n *o log x, which simplifies to n log x, where x represents the maximum value in the array. The final time complexity for the entire process is therefore n log x. Next, let's discuss the space complexity. The binary conversion step, bin_x, generates a binary string representation for each integer x. The length of this string is proportional to log x, but since these strings are temporary and discarded after use, they do not contribute to persistent memory usage. The primary space usage comes from Python's timsort algorithm, which requires n auxiliary space in the worst case for temporary storage during merging. This auxiliary space dominates the overall space complexity. Therefore, the final space complexity of the solution is n, which is efficient given the constraints of the problem. To put this into perspective, let's compare the optimized solution with a brute force approach. In a naive implementation, we would count the number of 1 bits for each pair of integers during sorting. This approach would require log x time for counting bits in every comparison, and with n squared comparisons, the total time complexity would reach n squared log x. The optimized solution, however, reduces the number of comparisons to n log n by leveraging timsort and the pre-computed key function. This improves the complexity to O n log x, a significant enhancement over the naive approach. Moreover, the time complexity remains the same O n log x for best, average, and worst cases, as the sorting algorithm and key function are consistently applied regardless of input ordering. In summary, the solution achieves a time complexity of O n log x and a space complexity of O n, demonstrating an efficient approach to solving this problem while avoiding the inefficiencies of a brute force method. When solving this problem, there are several common mistakes to watch out for. First, it's important to account for sort stability when numbers have the same count of 1 bits. If two numbers have an equal count, their relative order should remain the same as in the original array. Ignoring this can lead to incorrect results. To fix this, you can use a stable sort algorithm or include the integer value as a secondary key during sorting. Another issue is using inefficient bit counting logic. Repeatedly calculating the number of 1 bits for the same number can result in redundant computations. Instead, you can pre-compute the bit counts for all numbers in the range, such as from 0 to the maximum number in the array, and store them in a lookup table for faster access. Finally, don't overlook input constraints or edge cases. For example, you might encounter an empty array, an array with identical numbers, or very large inputs. Always validate your inputs and thoroughly test edge cases to avoid runtime errors or incorrect results. Another common pitfall is confusing bitwise operations. For instance, misusing operators like and versus or can lead to incorrect bit counts and break your logic. To avoid this, rely on well-tested functions like bin, x.count, 1 in Python and carefully check your operator usage. Additionally, keep an eye on the time complexity of your sorting step. Sorting the array is often the most expensive part of the solution, and for larger inputs, failing to optimize this step can make your approach inefficient. If you're working with a large array, consider alternatives like counting sort or bucket sort, which can reduce the complexity under specific conditions, such as when the range of bit counts is limited. In interviews, this type of problem often tests your understanding of bit manipulation and optimization strategies. A key insight to remember is that many bit manipulation problems require you to efficiently compute properties of binary representations, such as the number of 1 bits. It's helpful to practice techniques like bit masking, shifting, and pre-computing results to strengthen your skills. Interviewers also tend to look for an improvement from brute force approaches to optimized solutions. For instance, using pre-computed bit counts or leveraging sorting properties can demonstrate a clear step up in efficiency. Be prepared to explain the trade-offs in your approach. For example, you might discuss the time complexity of O n log n for standard sorting versus O n for counting sort, and how these compare in terms of space usage, such as when using a lookup table. Related problems that can help you practice these concepts include LeetCode 136, 191, 338, and 1046. These problems share similar themes, such as bit manipulation, sorting, and optimization. Finally, let's consider some alternative approaches to solving this problem. One option is pre-computing bit counts. This approach allows you to achieve O(1) lookups per number, which makes it very efficient during the sorting step. However, it does require additional space for the lookup table, so it's best suited for scenarios where the range of input values is small, such as integers between 0 and 10,000. Another alternative is using bucket sort, where numbers are grouped by their bit counts. This can achieve linear time complexity, but it comes with space overhead due to the need for additional buckets. This approach works well when the range of bit counts is limited, such as 0 to 32 for 32-bit integers. Lastly, you can use a custom comparator for sorting. While this simplifies the implementation, it relies on the standard O n log n time complexity of comparison-based sorting. This method is ideal for moderate-sized arrays where simplicity is more important than maximizing optimization. That wraps up our solution to problem number 1356, sort integers by the number of 1 bits. We covered the problem, broke down the approach, and discussed key takeaways. I hope you found this session helpful. Don't forget to practice similar problems to sharpen your skills. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!